Engineering here at the University of Iowa. And as I said, I'm delighted to welcome you today to our Distinguished Speaker event. We launched this series in fall 2020 with the intention of bringing in esteemed speakers who can provide their perspective on innovation in engineering education, the transformative power of engineering research, and the intersection between engineering and ethics, social justice, and equity. With this as backdrop, it is a great pleasure for me to introduce Michael Menzel as today's distinguished speaker. Mike Menzel is the NASA Mission Systems Engineer for the James Webb Space Telescope at the Goddard Space Flight Center in Greenbelt, Maryland. He's held this position since he joined NASA in June 2004. His involvement with the James Webb project extends back to 1998 when he was with Lockheed Martin. In his role on James Webb, Mr. Menzel oversees all system engineering efforts, which include requirements formulation and management, systems design and integration, and systems validation and verification. Mr. Menzel received a BS degree in physics from MIT in 1981 and earned an MS degree in physics from Columbia University in 1986 while he was working for RCA. During his career, Mr. Menzel has held various positions as an adjunct college instructor for astronomy and physics. He's an avid amateur astronomer and is a member of the American Astronomical Society. Colleagues, please join me in giving a warm welcome to Mr. Menzel. Thank you.
Well, thank you. I'm happy to be here. I'm happy to share with you what I've been doing for the past 25 years, the James Webb Space Telescope. Just a quick introduction to it. The James Webb Space Telescope is a true international collaboration between NASA, the European Space Agencies, and the Canadian Space Agencies, along with our domestic contractors, Northrop Grumman, Ball Aerospace, our academia. Here at the U.S., the University of Arizona provided one of the 4 instruments, and the ESA and JPL and CISA provided the other 3 instruments. In short, the James Webb mission is to put a deployable 6-meter telescope that operates at cryogenic temperatures at the L2 point, and we launched on December 25th, Christmas of this year. We're required to work for 5 years, but we intentionally put enough fuel on board for 10 years, and I'm happy to say, due to a perfect Ariane launch, we have enough fuel for over 20 years. So let me get first, I set this presentation up in the eyes and the perspectives of a systems engineer, and what I'm commonly asked is, what does a systems engineer do? So the first thing we do, which for me is the most fun, is to understand the science objectives. So I'm going to go over that with you. After understanding the science objectives, we, systems engineers, put that into a language that engineers understand, which is the language of requirements, something that must be done. After that, I'm going to show you the process that we use to design James Webb. Then I'll talk about the process. Now, while that design is going on, typically we do 2 other things. We do system analysis and performance assessments, which in this case is equate to integrated modeling. Technology development. This is what I'm going to have to shortchange today, but if you want to come up later, I'd be glad to talk with you about that. And finally, the verification of the as-built system, the proof that what we built is going to work once we fly it. And then finally, what I'm involved in now, happily, is to actually operate the system. So let's get started with the science of James Webb. Back in around 1995, astronomers got together and they came up with 4 basic themes that they wanted this next telescope, the successor to Hubble, to address. The first is to see the first galaxies that turned on in our universe. Astronomers will tell you that our universe probably began with a Big Bang about 13.8 billion years ago. Probably about between 100 and maybe 400 million years after that, the first galaxies lit up the universe. We wanted to build a telescope that would see those first galaxies, and it was nicknamed the first light machine because of that. Next, we want to see how galaxies evolve over cosmic time. When you look at galaxies that are close to our Milky Way, they look like that guy up there, that spiral pinwheel. That's M81. It has structure to it. But when we look very, very far away, very far back in time, the galaxies look like amorphous blobs, like you see in the lower part there. to know how those amorphous blobs, the early universe, evolves into the stars that we see. Next, we want to see how stars are born in our own Milky Way galaxy. Now, we know they're born in these cocoons of gas and dust called nebula, but visible light doesn't get through a lot of the dust. So we want to look at something that maybe could peer through the dust and see those embryonic stars being born. And finally, we wanted to learn how solar systems evolve. These were the 4 themes that James Webb was designed to back in 1995. Since that time, though, there was a 5th science theme that was added that was very topical and, luckily for us, didn't require any extra capability. Over the course of these many years, we've discovered about 5,000 exoplanets around other stars. 5,000 planets orbiting other stars, and we want to start looking at them and examining them in detail for signs of biomarkers, elements that are either caused by life or necessary for life. So James Webb was in a perfect position to start making detailed investigations of these exoplanets. So these were the 4 or the 5 science themes, and now it was my job to understand them and to write requirements as such. So mission requirements. If you're going to build a telescope, there's some basic questions that you want to translate for engineers. Spectral coverage, what colors should we observe? How big should these things be, which equates to radiometric sensitivity? How much light should we collect? It also equates to stray light signal-to-noise ratio, how much of the celestial sky or sphere should we see at any one time, and resolution and image quality, what's the smallest object that we can discern? These are the basic things that you would require if you're going to build a telescope. So the first one, the science of James Webb does not require a visible telescope like Hubble or like your eyes. It requires an infrared telescope. Why? If you're looking for the first stars that evolved in the universe, astronomers will tell you that those stars are probably very massive and therefore very, very hot. That means they're emitting a lot of blue light, blue shortwave light. But that blue light has been traveling through a universe that has been expanding for over 13 billion years. And because of that, that blue light, as it traverses that distance, gets stretched out like a slinky, so that by the time it reaches us, it's no longer blue light, it's long wavelength infrared light. So to see those first galaxies, we have to be an infrared telescope, which Hubble is really not. Second, if we want to see stars being born in our own Milky Way, those stars are born in those dust cocoons. Visible light does not make its way through that, but infrared light actually can penetrate dust. So we want to see those embryonic stars, once again, infrared. At the end, the science dictates that James Webb should operate in the region from about 0.6 microns to 28 microns in what astronomers call the near and mid-infrared. Next, how big does James Webb have to be? Now, James Webb wants to see the first stars in the first galaxies in the universe that are probably of the order of a nanojansky. And if you want to know what a nanojansky is, it's 10 to the minus 35 watts per meter squared per hertz, which is about as clear as mud to most people. So if you really want to know what a nanojansky looks like, take a child's night light. It puts out about 5 watts. Put it on the moon and look at it from the Earth. It will appear to be 20 nanojanskys. We're looking for something of that order of brightness. Well, how do you do it? Well, you got to create a big light bucket. James Webb had to be no smaller than about 6 meters across. And even at 6 meters across, it's only collecting 1 photon per second. And to put that in perspective, if you go out tonight, if the clouds aren't out, you might see a star called Vega. Your little eye will be collecting about 1 million photons per second from Vega. But that's only half the problem. The other problem is discerning these faint signals from the stray light that's already there. And that's a bigger problem that I had to convey to my managers that took a little time. The dust in our own solar system will be emitting 3 photons per second, the zodiacal light. So we have to pay very, very special attention to stray light. Okay, well, we can build telescopes of 6 meters in diameter. If you go to Hawaii, there's the Keck. It's about 10 meters in diameter. And ground observatories started to go to a new technology. Rather than building one big solid mirror, they went on Keck. Keck is built from 13 individual segments, all positioned and shaped to act as one big mirror. We'll do the same. And by the way, there's another advantage to that I'll come by in a minute. And even though we're smaller than Keck, we're at 6 meters and they're around 10, When you take into account absorption by our atmosphere, we collect more light than Keck. Now, they say never show equations in a public talk, but we're smart people here in the room. I can show you equations, but I'm not going to get into this. I am going to let you know, though, that usually there's one equation that dictates a systems engineer's life. This was mine. It's a relatively simple one. It's the signal to noise of detecting a very faint source. I'm not going to go into all the factors on it, but up at the top is the signal. Done everything I could for that. I made a humongous mirror. It's the stuff in the bottom, the noise, that you have to start worrying about, particularly two terms, background and dark current. Those two terms are temperature dependent. And that's going to play an important part in what I'm about to say now. But by the way, over the many years, I had to convince my own bosses how important straight control was, how important it was to control the noise in the denominator. I thought this would do it. It didn't, by the way. They don't care. They're worried about cost and schedule. This is what a 10 nanojansky source looks like after a 10,000 second exposure. Can you see it? It's there. It's exactly just above the background, enough to have a signal to noise detection ratio of 10. This should tell you that, if you know physics or math, that there's a big danger in subtracting two almost equal big numbers and pretending that the difference is reliable. This is what I tried to show that. This shows the importance of getting those background levels as low as you can, because the signal you're looking for is barely discernible above that. Now, the way we do that is we subtract out the background and bang, there's the star. But the reliability of that difference starts to become critical. Okay, so if you want to make the telescope such that it can detect these faint sources, in the infrared, you're going to have to make it cold. The bottom line is all of us are glowing at infrared temperatures. We glow very brightly at infrared temperatures. You don't want your telescope to glow brighter than the stars that it's looking at. So the telescope has to be cold. About 55 degrees Kelvin, minus 361 degrees Fahrenheit, all 3 metric tons of this beast has to be cooled to 55 degrees above absolute zero. Well, you're not going to fly a refrigerator to do that. The only thing you can do is build a humongous umbrella, a sun shield. That sun shield we're going to put out, it's not going to orbit the Earth. It's going to be out at the Earth-Sun Lagrange point, a point about 1 million miles away from the Earth. It follows the Earth around the sun every 365 days, and by putting it there, all of the 3 brightest objects, the sun, the Earth, and the moon, are all on one side of the spacecraft. One umbrella can block them all. Now, that one umbrella is no ordinary umbrella. It will receive about 200,000 watts of solar radiation, and it can only allow 0.02 watts to go through. That way, the telescope can passively cool to these temperatures. So I tell folks that has an SPF of 10 million. And if you think that's easy, believe me, it's not. And by the way, the sun shield also, in order to look over the entire sky, we have to size the sun shield such that we can point 5 degrees toward the sun, 45 degrees away from the sun. We can circle around the sun line, and at any moment in time, we can see 35% of the celestial sphere. Now, we get to see the whole celestial sphere as we go around the sun, and the constellations just go in and out of that annular region that I've just drawn. So over the course of the year, we get to see the whole sky. But by the way, sizing this means that umbrella is the size of a tennis court. Okay, the final requirement that we have to deal with is called image quality. And for those that aren't in physics, excuse me for a second while I diverse. Image quality has to do with the smallest amount of detail that you can discern. Now, if light was not a wave, if it followed straight lines and was a perfect ray, a lens or a telescope could bring all those rays to a perfect focus, and your image would be a perfect point, a bright, perfect point. But light is a wave. And when a wave sees an edge, you get these ripples. It's called diffraction. Those ripples are places where some of that energy gets diverted in bad directions. And it means that because of this diffraction, there's a fundamental limit on how good a telescope can operate. And rather than getting a perfect image, it spreads out into a blur pattern that we astronomers call a point spread function. And the width of that point spread function is determined by the wavelength divided by diameter. That's laws of physics. You can't beat it. By the way, in the general public, I like to show this picture of a star people see. People are surprised when I tell them that's not the star. The actual star was much smaller than that. All you're seeing in that picture is the blur spot, in this case of the Hubble Space Telescope. But that blur spot determines your smallest bit of detail. Now, everything I just showed you pretended that the optics were perfect. If the optics has defects in them, those defects mess up the way light is bent, and that actually broadens your point spread function, meaning you decrease resolution. In order to make sure that we don't decrease resolution that much, there's a kind of rule of thumb we use saying, make sure that the total amount of error that you have in your system is no bigger than about lambda over 14, wavelength, a 14th of a wavelength. If you stick to that rule, the additional width of the point spread function is very small compared to what's already there. And they say, well, you're diffraction limited. So for James Webb, we want to be diffraction limited at a wavelength of 2 microns. That means our overall optical error can be no greater than 150 nanometers, which for optical engineers, by the way, is a piece of cake. But to the general public, I generally remind them, hey, that's about 1/670th of a piece of loose leaf paper. But that's no problem. The other part that can screw up an image is jitter. And for James Webb, we set our jitter requirement, how much the telescope moves back and forth, to be an equivalent of about 0.007 arc seconds, 7 milliarc seconds, which is what Hubble does. And if you want to visualize that, put our telescope at the Capitol, put a laser pointer on it, put a penny at the Empire State Building, and we'll keep the laser on the penny. That's 7 milliarc seconds. And I'm happy to tell you, on orbit, we're doing more like 1 milliarc second. Okay, so these are the chief requirements that we engineers now understand. We begin to build a system. I'm not going to go, these are the charts that I'm going to go through very quickly, but there was a process that I used as the lead systems engineer for James Webb on how to design this thing, how to do trade studies, how to balance your alternatives. And it was a little bit radical for some of my industrial partners, but I stuck to it. I stuck to it by saying, in typical engineering, subsystem A is going to do his work and make his subsystem perfect. Subsystem B is going to make his subsystem perfect, right? They're all going to be perfection. And when you take 2 perfect subsystems and put them together, your chance of having a perfect system is nil. I said, no, I don't want to do that. I want all you trades, me, the systems engineer, the list of options. And I'll pick the list of options that are best for the system. Now, by the way, I had a lot of reason to do this, not the least of which was intense mass problems we had in the beginning of this. The other thing that I did, here's the list of all the trades we did. We must have done around 70 trades, all going on at the same time. And the thing about doing trades at the same time with a whole cadre of people who are just plain brilliant, motivated, and they want to be left alone, is that I was the flight controller. I kept track of all their trade options. I made sure that I understood which ones were exclusive of others, and we coordinated that. If we were a systems class, I'd go into more of this, but we'll just get through this. One of the worst trades that I did, that we had to put hot electronics on the cold side of the observatory. This was people thought I was crazy. This is a trade that I led. And the reason I thought I was crazy was, I told folks at lunch, we were tracking milliwatts through the system. And here I am putting ambient stuff on the cold side. The reason I did that was if we had the electronics boxes of the instruments on the spacecraft, they'd be almost 10 meters away. I started tallying up the amount of electronic noise that we were adding with those cables, and I found that was becoming a major source of noise. So we did trade studies, and we showed with the proper design and the proper installation, this was not only possible, I had my margin that I wanted. So this was one of the trades that I led, and it caused me many sleepless nights. As a systems engineer, I also kept track of the key parameters. I'll just skip through this one. And let's go. As part of putting together a very complex system, like James Webb, you have to rely on integrated modeling. On the models, between the structures, the optics, the thermal, the jitter and control systems. We had a very elaborate process for doing this. We called them integrated models. We'd put the design parameters into our models. This is what we would get out, which would be all the things that I wanted to get out to make sure my system is working correctly. And then we coordinated all the analysis and all the analysis interfaces that had to happen to make that happen. And it was a very, very elaborate process. And for anyone who wants a better discussion of this later, I'd be glad to talk to you about it. But it did require me and my team, the systems team, to do a lot of coordination with the people that were doing the complex models for this. And at the end of all this, this is the design that comes out. It stands about as tall as a 3-story building. It's a 6.5-meter telescope made of 18 individual segments, all gold-plated to give you high reflectivity in the infrared. The sun shield is about 21 meters long by about 15 meters wide. And it has 4 science instruments, all operating in the wavelengths between 0.6 and 28 microns. It has a mass of about 6 metric tons, 6,300 kilograms. And you do know at the top, it is bigger than any rocket currently available to launch it. So we have to fold it up to look like that, which is a nightmare. Here it is. There's all the parts of the telescope there. Behind the telescope, that's where the instruments are housed in a structure what they called the Integrated Science Instrument Module. And there's that ISIM electronics compartment, the IEC. That's ambient electronics that I put there. There's the sun shield consisting of 5 separate layers. You need 5 layers to get that SPF of 10 million. And then on the hot side of the spacecraft, facing the sun, is the normal stuff, the spacecraft bus, with all the traditional subsystems in it. And if you look at me next to our telescope, there I am. That's what it has to fit into. Yeah, I mean, it's funny, when I show this in the public, they think that's cool. When I show it to engineering schools, I get the laughter, which is the correct reaction. It has to look like that. The telescope itself is called a trimere anastigmat. It has 3 curved optical surfaces. And the reason it has that 3rd curved mirror, we call it the tertiary mirror, is to give this a big field of view. So we got a bigger field of view than even Hubble had. There are the 4 science instruments that we've flown. The first one, NIRCam from the University of Arizona, is a camera, shows the pretty pictures from 0.6 to 5 microns. The NIRSpec instrument from the European Space Agency is a multi-object spectrometer. It can take up to 100 simultaneous spectra of galaxies at the same time. The MIRI instrument from ESA and JPL is a mid-infrared instrument. It operates from 5 microns to 28 microns. And Canada provided our fine guidance sensor and the NIRS instrument. The NIRS instrument is a camera. It has a shorter or smaller spectral bandpass, so it gets better spectral resolution. And the FGS controls a pointing system that keeps the telescope pointed on its target. And then finally, the observatory, but obviously we have to design the whole system. So we start with the ground system. We're going to use the same system as Hubble. The Space Telescope Science Institute will be the ops center, and we'll use the Deep Space Network to talk to it. It will launch on the Ariane 5 launcher, which is a beautiful launcher. It's provided by the French. It was a gift in kind from the French and from Europe. Europe, in turn, we let them fly 2 instruments. It's a beautiful, and by the way, the rocket was perfect. The rocket puts us on a direct inject path out to the L2 point. On our way there, we'll do the deployments. And then we'll finally just literally fall into the orbit around the L2 point. And that's where we'll start to conduct our science mission. Okay, so here's the deployment sequence. This is the second worst 14 days of my life. This was put together by Northrop Grumman, and it shows the sequence that we use to unfold this thing in space. 50 of the most complex deployments ever attempted. We just come off the Ariane, we null our rates, point to the sun, get the solar array out so we're no longer running off battery. On the bottom, you can see where we are relative to the moon, which really doesn't have much significance, but they made this for the public, so it's kind of neat. After we do our last primary mid-course correction, our big mid-course correction, which is about the time we pass the moon, we start our deployments. The first major deployment is to deploy the front and back structures down. We call them the unitized pallet structures. They are holding the sun shield, those 5 layers. Those 5 layers are held in place by 107 release mechanisms, all of which are single-point failures. We then lift up the telescope a meter. For those that were at lunch with me, these are the covers that are unrolling. And if anyone wants to stay later, I can tell you a horror story about that. The covers unroll, and then 2 mid-boom assemblies, telescoping mid-booms, pull those layers out like the sail on a ship. And then using motorized pulleys, we tension each of the 5 layers. That's a trim tab to balance solar pressure. And then we start, well, I guess we're going to be deploying a couple radiators here. But the tripod that holds the secondary mirror unfolds. There's a radiator that helps cool the instruments. 1 wing and the second wing. We planned 14 days for this. We had some hiccups, but I'm proud to say we did it in 14 days, which was amazing. I mean, we were really expecting there to be more problems in this, and we rehearsed it hard, but luck was on our side, and the deployment was perfect. If you look at what our orbit looks like, I show the Earth, there's the lunar orbit, and this is what our orbit around the L2 point looks like. It almost looks like a kidney bean or such, and it's pretty big. We do all those deployments that I just showed you on the way out to L2. After we deploy, it takes about 30 or 40 days to cool down to those cryogenic temperatures. And once we're down at those temperatures, then we start to calibrate our instruments. That happens there. Then we fall into orbit. 6 months later, we're about there, and that's where we start our science mission. And once again, I'm proud to say we started it on time. We didn't have to. We were going to take our time commissioning, but we did start the science mission on time. Okay, so we designed it. It works. Here's how we verified that it was ready for flight, which was no easy job. First, we had to manufacture these things. Here's the mirrors being made. They were made and tested at the Marshall Space Flight Center individually at cryogenic temperatures. Those mirrors do not work well at optical temperatures, and I'll explain a little bit of that in a minute. Then we made the backplane structure. That is made of composites. We put the segments together on the structure at the Goddard Space Flight Center. And we had these black covers over them. And by the way, we had to put those mirrors on the structure robotically. You don't want to induce stress. You don't want to just bolt them on, because you could be putting stress, and that stress will show up as a misfigure of the mirror. You'll see that. Hell, I actually saw one guy, we actually left the piece of tape on one of the mirrors on the side. It was supposed to be there. We just forgot to take it off. We saw that tape on optical testing. We saw the stress it put into the mirror. Oh, and when we were all watching the first time, someone's hanging over our beautiful telescope on a diving board, taking the covers off. We all decided right then and there the covers are not going back on. We will keep the mirrors clean, but we're not dangling somebody over our beautiful mirror ever again. Here are the 4 instruments when they were delivered to the Goddard Space Flight Center. And these photos do not do them justice. This near-spec instrument over here is about the size of a queen-size mattress. It's huge. We put the instruments together in a common structure. We called it the ISOM. And that big thing on the right is the near-spec. As I say, that's about the size of a queen-size mattress. Then we put the instruments, we backed that down and mounted that to the telescope. Then we tested the telescope at ambient temperature, and the figure is horrible, right? We tested it at ambient, then we went and we shook the telescope. We brought it to the vibe chamber. Then we brought it back in, and we were looking to make sure that the shape didn't change. It was as horrible before as it was after, and it was. So then we sent the telescope down to the Johnson Space Flight Center into their Chamber A facility. That's one of the 2 largest chambers, thermal vac chambers in the U.S. It's about as tall as a 7-story building. You can see, to give you a sense of scale, there's some people right there near the doorway. We send the telescope in. We had very, very elaborate test setup in there to make sure that the telescope worked optically at its temperature, and it did. For those that like optics, that's the money shot. This is the one we all went gaga over. That's the interferogram, which if you know anything about interferograms, that looks lousy. But what it does look like, in a gravity field, that's what our models said a perfect telescope of this should look like. In other words, if you wanted to rate this as optically, you'd go nuts because the fringes should be straight lines. But when you accounted for the gravitational distortion, those lines were what we expected. This said, hey, we're ready to go. Meanwhile, back at Northrop Grumman out in Redondo Beach, they were putting together the spacecraft in the sun shield. And there it is for the first deployment test. And then finally, we became an observatory in 2019. Telescope met spacecraft. And let's see if this works. It does. By the way, while this is going on, my son was about 4 years old when I started this job. He's now one of the videographers. He took some of this video footage. I remember what he told me the day he comes in and says, Dad, I'm going to be photo video you take from your telescope. I said, for the love of God, stay away from that thing. It's $5 billion. God, I don't want to hear that something. They're just testing the deployments. Here's some of the beauty shots I think my son took. That's the IEC, by the way. That was that champion box. After this, we shipped down to the launch site in South America in September 2021. We mounted it to the rocket, rolled it out on December 23rd. And on Christmas Day, it stopped being an INT task and it started to be mission ops. There it is.
Tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage.
I can tell you, first,
one
one of the perks of dealing with the French launchers is you get a trip to Paris about twice a year. I don't know any French, which is a crime. But if I heard the words "sacre bleu" only once during this, I would have jumped out of my skin. But the launch was perfect. And 30 minutes after this perfect launch on Christmas Day, I got to say goodbye to the observatory that I was working on for 25 years. This was a camera aboard the upper stage of the Ariane launch. If you look to the right, you'll see that's Saudi Arabia, and I think they call it the Horn of Africa, going into the Red Sea. The push-off from the rocket was perfect. It was so perfect, the solar array popped out. I remember a bunch of reporters were following around that day. It looked like a dog not understanding. We weren't in the solar array. Not even a little. Why should I? It's because we told the reporters to come out 3 minutes after setting. Well, the computer on board said, hey, everything's rock solid. I'm good. Tip off dates. No. And it did. Well, let me get to some of the fun pictures. But if anyone wants to see the solar array coming out there, I'll show you. After that, we completed our commissioning on time. That commissioning had some very complicated portions to it. The launch, you've already seen the deployments. Those were completed on January 8th. The cool down. The cool down is something that you really, you might take for granted. But you have an infrared observatory. Water is not good. Water absorbs infrared light. And while you're cooling down, some parts are hot, some parts are cold. you got to make sure that the hot parts aren't emitting water that's going to condense on the cold parts like the mirrors. So we had to time our cool down profiles very, very carefully and monitor them very carefully during this. Then we started to phase the telescope, make sure those individual segments were all aligned. And then on July 12th of this year, we released our first images. And I got to be honest, I wasn't emotional until I saw some of these images. In particular, one sent me off to, really hit me. And it's this one. The first image we took, it's a deep field image, and it shows a massive galaxy cluster that's only about 4 billion light years away from the Earth, which is, cosmologically speaking, is next door. But that massive cluster, shown right here, is so massive it's bending space-time so much it's creating a gravitational lens. These distorted arcs that you see are the distorted images of galaxies much farther away, passing through that gravity field and bending. I haven't tried this at home yet, but I'm going to try it for future lectures. Taking one of those old spherical fish bowls, and if you hold it up and you look at things in the distance, I'm pretty sure that they will distort the same way. At any rate, when I saw this image, my wife, after they came out, I saw it a couple days before, and because I asked, what's the limiting magnitude on this? What's the dimmest thing you see? And when I saw that, I had goosebumps. And I'll tell you why right now. When my wife saw it, she looked at me and she goes, "It looks like Hubble." And it does. She was 1,000% right. The Hubble image that she's referring to took 14 days. This took 12 hours. We haven't even cranked this sucker up yet. So after I saw this, and they told me, I knew it was a 12-hour exposure, and they told me the limiting mag was AB mag 30. I got goosebumps, and all I could say to my friends was, we built this thing to see first light. What's ever out there, we're going to see it. Next, by the way, we know we actually broke Hubble's record because we took spectra of some of those galaxies to get their redshift. And we know that one of them is pretty much 13.1 billion. The light's been traveling for 13.1 billion years. That beats the Hubble image. Then we took this picture, this image of Stephan's quintet, 4 galaxies that are interacting, and they're actually going to merge. There's 5 galaxies in there. This guy over here is just an interloper. He's just photobombing the other 4. This guy, this guy, this guy, this guy, they're all interacting, and they will probably merge. Astronomers believe that galaxies evolve as small amorphous clumps that eventually start merging. And a lot of interesting stuff happens. For instance, you see this arc right here. That arc is a shock wave that's happening in the intergalactic gas as these galaxies start to tidally interact. And that's called what we nicknamed a starburst. Those are all new stars being born. Then we showed this, they called it's the Carina Nebula, got nicknamed the Cosmic Cliffs. These are places in our Milky Way where star birth is happening. If you looked at it with a small telescope, it would look like that. That's the region that we photographed. This, outside the field of view here, there are very hot stars that are probably up around here. They're newly born, but very hot. They're actually evaporating the cloud of gas that they came from. And what you're seeing here is the evaporation front. Places like this, where there's higher density, so that's evaporating less, and it's forming one of these great columns. And then they found there's a new star being born right there, and there's some cosmic or jets that are happening in new stars. So we're already piercing the dust to see these embryonic stars and what's going on in them. This is a star that's dying, the Southern Ring Nebula, in both the near-infrared light and the near-infrared light. And this one isn't so appealing to the public, but this is a spectra of an exoplanet showing the spectrum and the absorption features of water. So we know there's water on this exoplanet. The interesting thing was, Hubble knew this, but when they looked at the exact profile of the absorption lines, that was the first concrete indication of not only water vapor in the atmosphere, but water clouds. The existence of condensed water clouds start to broaden out the absorption features. Since these initial images, we've had a plethora of other images that are coming out all the time. My favorite, though, which even beat the deep field, was this guy over here. When I saw that, I was with a planetary astronomer, and we went nuts. That's not Saturn, in case you don't know. That's Neptune. Neptune, we all know, has pathetic little dust rings. The only reason we know they're there is every once in a while a star passes in behind them and we can see the starlight dip. Look at those things. It was beautiful when we saw that. Even the planetary astronomer went nuts on that. Technical challenges, this is where I'll sum up. What's hard about this? I had some reporters coming up to me and say, you made it look so easy. Well, that was luck. Okay, we did everything we could to prepare for this, but don't underestimate luck. And anyone who says that there wasn't luck involved is either a liar or a fool. But we did, we had the guts to try. The first thing that was hard are those deployments. Those are sick. Those are the sickest deployment. Over 50 major deployments, 178 release mechanisms, 155 motors, 600 pulleys, over 344 single point failure items. If any one of them failed, the mission was over. And the only thing I can say about that was I knew it. Me and my team took special precautions. We understood the failure modes, the way the failure would happen. And the majority of those failures would happen in the way they were installed and set the last time, much like a parachute. So what we did was we took special precautions. We filmed the installation. We filmed and videoed the installation and photographed it. And then we all reviewed the video records to make sure they were installed correctly. There were a bunch of other inspections that we did, but we concentrated on those. The other thing that I wanted to point out to people is how long it takes to fold up that sun shield. It was about 3 months to fold it. Look at it. It involved about 3 to 4 cherry pickers, about 3 stories tall. And, we had to really debate how many times we would actually practice this test. Headquarters wanted us to keep testing and testing and testing. And I was on the other side going, every time we test, we risk damage and we do damage. There's a sweet spot here. And I think we found it. Making 3 metric tons of telescope 55 degrees above absolute zero is another thing that consumed me. By the way, this is just for fun. We had detailed thermal maps, detailed heat maps of every damn half a watt that was traversing this observatory and keeping track of them to make sure that we understood it. And even when we understood the thermal architecture, going to cryo has a lot of problems. First, when you polish a mirror, you'll probably polish it at ambient. And then you'll take it to cryo, and it will distort. It'll distort big time. So the trick is, you polish it ambient, you take it to cryo, and you find out where all the hills are. Bring it back to ambient. Polish out the hills and put valleys there. And if you do it just right, when we go to cryo, it'll assume the right shape. It's called cryo null figuring. It took us, in the beginning, about 3 to 4 iterations to get it right. Then by the end, we were doing it in 2 iterations. Next, the things distort, things contract at different rates going to cryo. Beryllium doesn't really, beryllium contracts quite a bit, the beryllium mirrors, but the composite structure that holds them doesn't contract much at all. You want to make sure that the relative contraction doesn't flex or distort your mirrors. So we had to carefully design the flexures. And finally, things that go to cryo, they ring like a bell. So we have mechanisms on the spacecraft called reaction wheels that could cause some vibration. That vibration doesn't tend to damp out at cryogenic temperatures. It tends to transmit. So we had to put special dampers on board, magnetic dampers, to do that. My point is, cryo was a nightmare. And finally, just testing the telescope. The third major challenge is testing it. There's a philosophy at NASA, test as you fly. Great, because you find the unknown unknowns. You can't test this as it flies. It's a 6-meter telescope. If I want to create a star for a 6-meter telescope, I need another 6-meter telescope, a collimator. Oh, and by the way, they both have to be cryogenic. So, hey, headquarters, can you fund me another 6-meter cryogenic telescope? Come on. Then we had to build in that chamber down at Johnson a gas helium shroud to get as close to operational temperatures as we could, 23 Kelvin. It was close enough. Then that has to be in a big chamber. But the observatory the hot side of the observatory operates at ambient, so you better make sure all those hot ambient photons don't find their way to the cold side. And this thing can't support its own weight, so you got to put structure to offload gravity. And you got to make sure that structure doesn't conduct heat to the cold side. It's a nightmare. You can't test this as it flies. So what we had to do instead was do tests at lower levels, correlate our analytic models to those tests so that we had a model of the telescope that says, yeah, the model predicts its behavior. Yeah, the spacecraft model predicts its behavior. Put them together and have that predict how we would do on flight. Now, that sounds easy, but models don't predict and don't simulate workmanship errors. So I had to fight with headquarters through this whole thing to make sure I had enough margin to account for reasonable workmanship errors. And you had to be very careful on that because some parts are very sensitive than others. But in the end, it worked. In the end, I want to just close with this. I wanted to be an astronomer since I was 6 years old. I came pretty close. I wanted to work at the Palomar telescope, the largest telescope, 5 meters across, when I was growing up. I consider myself extremely lucky to have been part of a team that built a telescope bigger than Mount Palomar, not located in the hills of San Diego, but located 4 times farther than the moon. I've been on this job for 25 years, and I've had the honor and the privilege of seeing it evolve from cartoons to detailed designs to hardware to wave goodbye. The telescope is now one of the premier astronomical tools of the next couple of decades. It'll address some of the fundamental questions before us. The first stars and galaxies, star formation, solar system evolution, search for habitable planets. It's truly a first of its kind space observatory and has offered system engineering teams some of the most very unique and difficult challenges. It'll rewrite the books on astronomy and engineering of future space observatories. And just as a closing thought, although on December 25th, I waved goodbye to my observatory as an observatory for the last time, if you have about a 16-inch telescope, it's still out there and you can see it. So I thank you for your attention. I'll take any questions you want, and that's it. Thank you. Questions? Oh, okay.
Well, the first question is, well, clearly it's been in the news lately because of the strike of the. So, how did you deal with that? Because we still see pictures coming out and they look great, and that was unexpected for you. So,
let me talk about the dreaded meteor strike. We knew that we were going to be struck by meteors, and we estimated the rate, and we are following the rate. We've been struck by about 14 micrometeoroids. And to put what a micrometeoroid is in perspective, the average micrometeoroid has a mass of about 1 microgram, and it's probably, I don't know, a thousandth or hundredth or a thousandth of a millimeter in diameter. But the problem is, these little dust particles, and that's all they are traveling at about 30 kilometers per second. Okay? We got 14, and the damage that we saw from the 14 was perfectly in keeping with what we expected. No, 13 of the 14 was perfectly in keeping with what we expected. There was a 14th, or one in the middle of there, that showed a little more damage than we had anticipated. We don't know why. It could be a statistical anomaly, and so far that looks like the reason. Even after those 14 strikes, we are still twice as good as we are supposed to be. We budgeted for these strikes, and right now the requirement said be diffraction limited at 2 microns. We are diffraction limited at 1 micron after those 14 strikes. The thing that got people, including me, woke us up was, is that one strike, is that a statistical anomaly, or should we count on that? So we're just going to watch it. But for the moment, all the margin that we had, and the reason systems engineers have margins for unknown unknowns, this is one of them. My boss that had been busting my behind for like 20 years, oh, Menzel, you're hoarding margin, you're hoarding margin, you're hoarding margin. He called me up after that, and he said, the night after that hit, and he goes, are you worried? I'm going, no, Bill, I'm not worried. You know why I'm not worried? Because I got a 100% margin. I'm going to go to bed at night and sleep. How about you? And he chuckled. He knew I was throwing it in his face, but we're not worried about that. If we saw that we would be getting hit continuously by that, I would still not be worried. because I think we calculate I would still make my mission success life of 5 years. One other thing about that, the degradation of those meteors is not going to fall off a cliff. It'll be a graceful, even if we get hit by some that more than we expect. Well, you'll go from being a diffraction limited telescope of 1 micron to 2 microns to 2.5 microns to 3. It's still a world-class telescope. So I'm really not worried about that yet. Any other questions? Yep.
Any students?
Oh, don't be afraid.
Any students want to go ahead of Professor James Webb? Don't be afraid. It's okay.
Well, go ahead. You got another one?
Yeah, is there something peculiar about L2 that you would suffer? Because
No.
Has Hubble suffered?
No. Here's the story behind that. First, Hubble has a tube around it. That tube protects you. I mean, anyone on James Webb see 2 pi steradian. That means it can get hit from anywhere in the hemisphere. The Hubble tube means that telescope can get hit from a narrow cone. The tube protects it. James Webb could not have a tube because the tube would trap the heat. So we couldn't have had the tube. Second, people ask me the other question, whether the L2 environment is different. The L2 environment is cleaner. The low Earth orbit has all that junk that we've been depositing in it for 50 years now. So, and even if we weren't, the low Earth orbit is at the focus, is inside the Earth's gravity well, which attracts stuff. The L2 point does not have man-made gunk around it. And the gravity well of that is more, if you're familiar, it's more like a saddle point. So it's not as focused. So the L2 point's actually a better point. The next telescope that my friends and I are starting to doodle right now, which will be an optical telescope, it won't be ambient. We're hoping it might be something around 9 meters. We want a tube around that. So.
Let me ask you a really dumb question.
You haven't asked any dumb ones yet, so go ahead.
So where do you know, how do you know where to look for your first light? Because I assume the universe is isotropic, right?
Yep.
And so clearly we imagine that the Big Bang was in a certain, well, there was no space-time, but it was in a certain location in space-time.
It wasn't, by the way. But people hate that.
I hate
it's
that.
everywhere, right? Everywhere's Big Bang.
Exactly.
Right.
If it was a Big Bang and there was a singularity, then we imagine that the universe is much larger than that singularity, and therefore we should be peering into some hole to watch.
Yep.
So that's my mind's eye, but clearly the universe is isotropic. So
Right.
where do you look?
The answer, that's a great question, and the answer is real easy. We do believe that the structure of the universe is isotropic, so anywhere is as good as anywhere, right? So let's look at the regions outside the gas disk of the Milky Way. We try to look away from the Milky Way and what they call the galactic poles, or there are other places where we know that there are voids in the Milky Way's dust. I'm going to get this wrong. I think it's called the Holman Hole or something like that. But there's regions where astronomers know the Milky Way has hardly any dust. Look through there. And that's all the Hubble deep fields. They were all chosen because the Milky Way doesn't have a lot of dust in those directions. So, but you're right. Any place would be as good as any. But we just look for the places where the Milky Way and our own solar system. One of the places that astronomers like to look at is called the ecliptic poles, outside of the plane, perpendicular to the plane of the solar system. Yes?
Yes, thank you. I was curious if you could just talk briefly about the exoplanet analysis ability of James Webb. I know that exoplanets are hot. Actually, some exoplanet hunters were actually built at a small company in Iowa City, and they're deployed now. But then when they see an exoplanet, it's basically fed into a system. So what can we see with James Webb looking at exoplanets? I know you mentioned spectroscopy. How does that compare to our previous resources?
Well, James Webb has much greater spectral sensitivity than what we've had in the past. And the way they observe that is by looking at a transit. when the planet goes, picture the star, when the planet goes in front of the star, it causes a little eclipse, right? So you can see a little dip in the light. But when you look at the dip in the light in different colors, certain colors dip more than others. That's an indication of a spectral feature. For instance, if I put a planet with a good atmosphere that had a lot of oxygen in it, right? Well, when that planet goes in front of the star, I would see the starlight dip more in the oxygen spectral bands than in other bands. So that's how they're looking at this, and that's how they saw the water band in that. So they're looking at the transits. Now, a transit, a little planet going in front of a star causes only a very, very small dip in brightness. So you need very, very good sensitivity, one, to detect the dip, right? Then, if you're spreading that out into a spectrum, well, at any one wavelength, you're even getting less light. So the thing that James Webb has that the other telescopes don't is the incredible spectral and the incredible sensitivity. It's in space, and it's 6 meters in diameter. And we had a good feeling that that would be enough to do this. The other thing that James Webb has to do is it has to maintain stability. So it's the same before and after this transit. Things don't change. So, so far, the rumblings that I'm getting around the hall is that the stuff that we're seeing from James Webb transit science right now is much better than we thought. It's much better than we thought because Webb is behaving twice as good as was spec to. So when reporters used to ask me, what are the 3 things I wanted Webb to do? I said, well, I want to see first light. That, when I started this in late 97, it was called the First Light Machine. I wanted to see that. I want to actually tell my grandkids someday that I worked on the telescope that saw the first evidence of biomarkers. That's the second. The third thing I said is, I hope we start something totally new that we never even thought of. I had dreams of I have a master's in physics. I had a dream of maybe working on James Webb for 10 years, going back and get my PhD. Right? Well, it's 25 years. I'm 62. My shelf life is probably about over. But if they'd opened up a new branch of research, that would be so exciting to me, if only to say I was a part of starting it. So those are the 3 things. Anything else? Oh, yes, sir.
All right, I just wanted to start by thanking you because I've been hearing about James Webb literally as far back as my first memories go. So it was probably the greatest Christmas present NASA's given us yet. But I also did want to ask, you mentioned on the SMAC cluster that it took about 12 hours to reach the equivalent of the Hubble exposure. And you also mentioned that as the L2 point moves around the sun, you can see about 33-ish.
35.
35.
Yeah.
So there's those bits to the north and south in the poles that presumably are visible all year long.
Continuous viewing zone. That's very good. Yep.
But for the non-continuous viewing zones, how long can you keep yourself pointed at a single target there? Is it limited by the Earth's rotation around the sun, or is there some other factor going on? And do you think you'll even need the maximum amount of time that you'd have based on that orbit to get the science you want?
Okay, so the first thing is, it is limited by the amount of time that you can see an object is limited by the Earth's revolution around the sun. It's also limited by your ecliptic latitude. I can show you the continuous viewing zone, you're absolutely right, is 5 degrees around the ecliptic pole. But then you could go anti-sun, I think it may be 20 degrees, and still have an almost continuous arc before you cut off. And that would mean, you'd have over probably 7 months of visibility in that. In the annular part, you would be going in and out. You'd have about a month in here, and then a month on the other side, which is more than enough. The deep fields that they're planning on are going to be exposed for about 10 days, 5 to 10 days, which will be more than enough. And I was told that deep field is coming up in December. Now, there's rules about the way that it will be released. The scientists that put in the proposal have, and forgive me if I get this wrong, but roughly about a year to publish their data. After that, it goes public. So, the scientists that are doing the deep field, I'm not sure who they are, but they might take a little while to publish their data on that. But, and I'm not supposed to see it. The astronomers hate me because I know astronomy. I'm an engineer, but they know that I know what I'm looking at. I bet you I'll see that before they do.
Why don't we take one more? Let Dr. Wong have the honors of the last question. Maybe take another couple minutes.
So you're obviously taking a photo of three-dimensional space and putting it onto a flat picture. Just curious, are you using like the change in wavelength over the time of the exposure to figure out how far certain stars are?
Not the change in wavelength over the time of the exposure, but the wavelength is static. Now, here's what I mean by that. We know the colors that hydrogen emits in, right? And then they're not going to change. So if I see a galaxy and I look at the thumbprint of hydrogen in that galaxy's spectrum, and that wavelength is shifted by some amount, let's say it's shifted by a factor of 2 or 3. Well, astronomers say if it has a redshift of 3, it's this far. Another galaxy where I see the same hydrogen, but its spectrum is shifted toward red by 10. So I say, well, it has a redshift of 10. It must be this far. So it's just looking, we can tell cosmological distances by looking at known spectral features, hydrogen, helium, things like that, and looking how far they're shifted into the red. Because we know that it's a very simple phenomenon. As that light travels to us, it's getting stretched out like a slinky by expansion. So if the longer that light has been traveling through the universe, the more it gets shifted. And the longer it's been traveling, the farther it is away. It's as simple as that.
So is that going to limit how far into the past, I guess, you can see?
To a degree. That's why we made this infrared, because hydrogen, we're expecting blue light to be, to be red shifted by a factor of maybe 15, maybe 20 tops. If it gets shifted more than 20, the laws of physics as we know it are screwed up, and I would love that because then it's like virgin territory, right? I can probably write a paper and it might get published. But basically, we designed Webb so that it goes into the far infrared, and we can't expect red shifts that high and still have the laws of physics as we know them.
Mike, this has been amazing and inspiring. Thank you for joining us. Please help me thank our speaker once more.
Okay, thank you. Thank you. My pleasure.
Yeah, thank you for being here. I'm sure people may have a couple of questions.
They can ask me any question they want.
Okay.